We will start with uh, what we studied in the last class. We'll start with just have a recap of what we studied in the last class. We started with timers and counters, right? I introduced to the two timers, timer 0 and timer 1. Both these two timers are 16-bit registers and it is comprised of two 8-bit registers, right? The TH0, TH1, right? TL0 and TL1, right? What we saw that the lower byte and the higher byte registers. And also in order to support with the working of this timer 0 and timer 1, we use two SFRs, right? One is the TMOD register, which is used to control the various modes of operation of timer 0 and timer 1 here, right? And this TCON register, what we have, this controls the operation of the timer 0 and timer 1, right? We studied about the TMOD register, right? We know the SFR register, internal RAM address for that, right? And also if you see this one, what we studied, I said about the importance of the gate signal, right? What is about the gate signal, right? The gate bit is important to control, to run, to start and stop the timers here. You can see from this diagram what we have it, right? The diagram what we have it, you can see from this one is that you can see that when the gate signal is 0, if you see the circuitry for this one, when the gate signal is 0, the output of the inverter will be 1 here. So that irrespective of this one, irrespective of this pin, what is this pin we have? External interrupt 0 or external interrupt 1 pin, right? We have irrespective of this one, the output of this OR gate will be 1 here, right? So that when the gate signal is 0 here, now as I said here, the timer is enabled whenever the TRX control bit in the TCON register is set to 1. So that you can see that the output of the AND will be 1 only when these bits, right, what we have, the timer starter bits, what we have, TR0 and TR1. TR0 is for timer 0, TR1 is for timer 1. If those bits are 1, the output will be 1 and the switch will be connected here, right? So that, and this timer, the clock pulse will be given to the next stage of the timer circuitry there, right? We studied about this one, and this, when the gate is 0, the timer could be stopped with the help of TR bits, right? If the TR1 is set to 1, it will start the timer 1, and if the TR bit is equal to 0, it will start the timer is equal to 1, it will start the timer 0 here, right? And also when the gate bit is 1, and also when the gate bit is 1, the timer is enabled only when the INTX, the external interrupt 0 and the external interrupt 1, which is for timer 0 and timer 1 respectively, right? If that is set, that is high, the timer 0 will run, and if the INTX 1 is high, the timer 1 will run here. You can see from this circuitry what we have it, you can see at the bottom, right? Now it here, when the gate is 1, the output of the inverter will be 0, and when this is 1, the output of the OR gate will be 1. When this, the external interrupt 0 or the external interrupt 1 pins what we have, if that is set, the output of the OR gate will be 1. And you can see that the output of the AND will be only 1 when the TRX bits is also set here. It means that in addition to this external interrupt pins being set, you need this timer starter bits also to be set. Then only the output of this the AND gate will be 1 here. So that when it is 1, the switch will be connected here, and the clock pulse will be given to the next timer stage here. And this is what I discussed in the last class. This is when the gate is 1, we call it as a hardware way of controlling the timers. When the gate is equal to 0, it's software way of controlling the timers there, right? And also we studied the importance of the C/T bit, the timer or counter selected. You might have know, as I say here, right? When I say when I say the timer mode or the counter mode, the main difference is that whether the clock signal is internal to the 8051 or the clock signal is external to the 8051 microcontroller there, right? If the CT is 0, it means that the timer is in timer mode there. The timer is in timer operation, and the clock source is a crystal frequency of the 8051 microcontroller, and it will count the internal clock pulses there, right? Right. And you can see from this one what we have it, when the CT is equal to 0, when the CT is equal to 0, the switch is connected to 8 here. You can see the switch yes here, which is connected to A. So that A is connected to what we have, right? This is 8051 crystal oscillator, right? And divided by 12 here. So why we divided by 12? Because each pulse is one machine cycle now, right? Because we know that one machine cycle is in 8051. One machine cycle is made up of 12 clock pulses. When we divide it by 12, it means that the clock pulse what we apply to the timer is what? One clock pulse. So that one clock pulse is equal to one machine cycle to the timer what we apply there. So that you can see from this one, when this C/T bit is 0, it is connected to the internal clock circuitry here, what we have it, right? When I say C/T bit is equal to 1, the timer is in the counter operation and counter operation. And so that the counter is when it is used to count the external events there, external clock pulses there, right? As an and where from where you get the external clock pulses, you get the external clock pulses from external timer 1 input, external timer 0 input. What we have, this is T0 and T1 here, right? We get the external clock pulses. External clock pulse are the external clock sources are connected to these pins, and this T0 is for timer 0, T1 is for timer 1 here. As you can see here, when the CT, you can see from the diagram, when the CT is equal to 1 here, the switch is connected to B here. So that where is the clock source? Where is the clock source for this for the timer now? It is from the external signal on T1/0 pin here, which is nothing but external timer 0 input or external timer 1 input here, right? Right. As I said, the main distinction between the timer mode and the counter mode is whether the clock source is internal or whether the clock source is external here, right? You understand the importance of this C/T bit here. And also we studied about the mode signals M1 and M2, right? As we know that, right? For timer 1 also we have these two bits, and for timer 0 also we have M1 and M2 bits. Depending on these combinations, the timer could be operating in mode 0, mode 1, mode 2 and mode 3. What is mode 0 here? It is 13-bit timer mode here. And we know how to calculate the timer's clock frequency. We saw a couple of problems and how to find the period for that, right? When the clock source is internal, and the internal source what we have is normally, if you see normally what we hear is 11.0592 megahertz. And this is what the clock source what we normally use it. The one of the reasons why we use 11.0592 megahertz clock source is that because in order to communicate with the system like IBM PCs, right, having this as a crystal frequency, right, it will generate a baud rate which will provide, which will have minimum error or no error in communicating with the IBM PC. That's the reason we use the crystal frequency as 11.0592 megahertz, right? And also we saw about this one, right? Depending on the value what we send in the TMOD register, we know whether which timer is operating in which mode, right? And also we'll study about the TCON register, right? We know about the TMOD register. The TMOD register is used for what? To control the different modes of the timers, right? Whether it is mode 0, mode 1, mode 2 or mode 3 here. Here the TCON, and also we know that the TMOD register is byte addressable, right? You cannot have bit addressable there. But when it comes to TCON register, this is bit addressable also, right? So that you can address directly the one of the bits of the 8 bits what we have it in TCON registers there. You can see from this one what we have it, right? This is an 8-bit register, and also you can see the lower 4 bits, the lower nibble what we have. These are for interrupt pins. Interrupt in order to work with the interrupts, right? These 4 bits are used. The lower nibble which is used here, and the upper nibble what we have it. The upper nibble what we have. This is for the timer 1 and timer 0 to control the operation of timer 0 and timer 1 here. And also you can see that the bit 4 and bit 5 what we have, TR0 bit, TF0 bit, right? These is for timer 0, and also bit 6 and bit 7 what we have, TR1 and TF1. These two bits are timer 1 here, right? And what is this TR01 here? TR is nothing but what, right? As you can see from this diagram, the TF1 what we have, it is a timer 1 overflow flag. TR1 is nothing but the timer 1 run control bit, timer starter bit what I said, right? It is a timer 1 starter bit. Similarly, what we have, TF0, this is timer 0 overflow flag. Whenever the timer 0 overflows, right, whenever it reaches its maximum count values, or whenever it has a maximum count values, it has to reset to 0 0, right? Before resetting to 0 0, what it will have, it will set in the flag here, right? And the timer 0 will set this flag TF0 here, and the timer 0 will set TF1 flag here, right? This is, and also as I said, the TCON register is bit addressable. You can directly mention TCON.7, TCON.6, TCON.5, TCON.4 in the instruction itself, because these are bit addressable. You can easily call by the bits there, right? As I said here, the upper nibble is for the timer and the lower nibble is for the interrupt function here, right? And also you can see from that, now how to set it, how to set and clear, how to start the timer bits and how to stop the timer bits, right? We can see from this one what we can is, all are these are bit addressable. You can directly mention there set bit TR0 here, or also you can use instruction as set b tcon.4 here. When I say set b space TR0, what you are doing, you're setting this base so that TR0 is equal to 1 here, right? And again what we have, clear TR0, right? It means that when I say set b TR0, it means that you're starting the timer, you're starting the timer there. Which timer you're trying to start it here? It is timer 0 here, because it is TR0. Clear TR0, right? Clear TR0 means you're setting the value of TR bit to 0. It means that you are stopping the timer 0 there, right? And also what we have, set b TF0. What do you mean by set b TF0? You're setting the overflow flag for timer 0, right? Similarly, you're clearing that flag here. And also for timer 1, what we have it, similar to that one, what we have, set b tr1, clear tr1. When I say set b tr1, understand that you're starting the timer 1. When I say clear tr1, you're stopping the timer 1 there. And you can see the instructions on the right side of the equal sign here. All these are bit addressable. You can directly call this tcon.4, tcon.5, or tcon6, or tcon7 there, right? This is about the tcon control register, right? And also what we studied is of the timer mode 0. What is timer mode 0 here, right? Out of the 16 bits, we use only 13 bits for the timer here, right? Only 13 bits are used to count the number of machine cycles. Here, when I say number of machine cycles, one machine cycle is equal to one clock pulse here. When I use, because we know that we divided that by 12 there, because everyone remembers that one, right? And whenever it reaches this maximum, since it is only 13 bits, the maximum machine cycles it can count is what? 8191. And whenever it reaches this value, what will happen? It will overflow to 00 there, right? Since it is overflow to 00, it will set the overflow flag in the TCON register, right? Take an example. If it is timer 0, after reset, which flag bit will be set here? It is TF. If it is timer 0, it will be TF 0. If it is timer 1, it will be TF 1. That bit will be set after overflow, right? After the timer is reset, whenever the timer reaches this count 8191 for mode 0. We studied this in detail. I explained about this operation also. And here this is what the maximum, since it is 16 bits, what we can have is 0001, and all are till here. The 13 bits, what we can have from 0 to 13 bits will be set to 1, which will be 1F FFF. After that, it will be reset and it will be overflowed with, and it will be reset to 0000 H here. So that when it is reset, it will set an overflow flag, right, to 1 there, TF0 or TF1, depending on whether it is timer 0 or timer 1 there. This is about the mode, timer mode 0, right? The next what we have is timer mode 1 here, right? What is timer mode 1, right? Here, as I said in here, we use all the 16 bits are used to count the number of clock pulses here, right? And also we know that in order for the timer to work in mode 1, this M1 and M2 bits in TMOD register are set to 0 1 for timer X, right? If it is, take an example, if it timer 0, right, the lower bit 0 and bit 1, right, the bit 1 should be 0, and the bit 1 should be 0, and the bit 0 should be 1 there for timer 0 to operate in mode 1 there. Similarly, for the timer 1 to operate in mode 1, what you do that? We know that bit 4 and bit 5 are M0 and M1 bits for timer 1. So that what we have, the bit 5 will be 0, the bit 4 will be 1, right? So that you make sure that in TMOD register you go and set the value, so that the respective timer, whether it is timer 0 or timer 1, will be operating in mode 1 there, right? The mode bit should be 0 1. As I said here, this will act as, here the timer 0 or timer 1 is used as a 16-bit timer. All the 16 bits are used to count the number of clock cycles, the number of machine cycles here, right? Timer registers TLX and THX behaves as 8-bit up counters and collectively as 16-bit up counter here, right? This is the lower byte what we have. TLX is the lower byte, right? And THX is a higher byte what we have it. And collectively these two registers, this is 8-bit and this is 1 byte, and this is also 1 byte, right? This is 8 bits and 8 bits. Totally it will be 16-bit up counter. So that what is the value what we can have? We can start with an initial value of 000H2 FF, and whenever the counter counts the number of machine cycle to be FFH, it will be reset, right? It will be reset to 0000, and it will set the overflow flag to 1 in the TCON register. So that what is the maximum value what we can have it here? 65535 values, right? The timer is reset after this many machine cycles here, right? We'll understand the operation of timer operating in mode 1 here, right? We know that if the clock is 0, right, if the C/T bit is 0 here, right, we know that the clock source is internal clock source, the crystal frequency what we have it in 8051 microcontroller, that is connected here, right? And depending on start or stop control, how do you can start a stop control, right? It could be software control or a hardware control. In software control, what we can have? The TR bits, right? If the TR bits are set for that respective timer, the switch will be connected here. The switch will be connected here, and we can how we can start or stop. As I said here, set B TR0, set B TR1 bit. When I do that, you are setting those bits so that, and if the C/T bit is also 0, what will happen there? Right, when the gate signal is 0 there, now the clock pulse, this switch will be connected here, right? So that what we have is clock pulse, and the clock pulse is given to the timers here. It could be timer 0 or timer 1. X stands for 0 or 1, 0 or 1, right? So that we know that each of these two uh, uh, registers are what we have, 8 bits, right? The TLX is 8 bits, the THX is also 8 bits there. Now first it will uh, for each clock pulse, right, it receives, the timer will increment the number of counts what it has. Take an example, the initial value in TLX register, whether it is 0 or 1 register what we have, the initial value will be 00. That is 8 bits, right? 00H. And whenever it retrieves one clock pulse, the TLX register will increment by 1, so that it will be 0 1. The next time it will be 1 0. The third clock pulse what it reaches, it will be 1 1. Like this is how it works there, right? If you know that it is an 8-bit register, what we have it, right? 0 0, it will keep on incrementing 0 1 2 3 4, right? The maximum value what we can have it in 8 bits is what, 7 F. Till that it will keep on incrementing. Once it is done, it will increment the higher bits what we have it, so that it is acting as an 8-bit counter, and this is also acting as an 8-bit counter, and collectively it is a 16-bit counter what we have, and it will count from what, 0000H to FFFFH, so that you can see in the diagram what we have, as the number of clock pulse to the timer keeps on increasing, right? It keeps on receiving the clock pulses, the counter will increase its value from 0 to, right, you can see that 0 to 1 2 3 4 5, and how many counts it will count to, it will count to a maximum of 65535 there, right? And whenever the count value is this one, so that in that value, the timer value what we have it, if the value is in hexadecimal FFFH, what will happen, the timer will reset and it will set the overflow flag here. Overflow flag will be set. Maybe if the interrupt is also enabled, it will raise an interrupt also there, right? Everyone understood? This is about the timer mode 1 operation. As I said here, the maximum machine cycles it can count is 65535, and whenever it reaches that one, again it will be reset to 0 there, right? And again it receives the clock pulse, it will keep on incrementing. Everyone understood about the mode 1 of timer operation here? The entire 16 bits are used to count the number of clock pulses here, right? And whenever it reaches the maximum value of FFFFH, it will be reset to 0. It will raise the flag in the TCON register, and also if the interrupts are enabled, it will raise an interrupt there, right? This is about the timer operating in mode 1, right? It could be timer 0 or timer 1 operating in mode 1 here, right? Now, how do you generate the time delay using the timers operating in mode 1 here, right? Now, if I want to have some delay, right, how do you generate that time delay using this timer mode, right? The steps what you need to follow is, the first is load the TMOD value register indicating which timer here. As I said here, you can see from this one, now I need to generate the time delay, and which mode I need to use for this one. I need to use mode 1 for this one, right? Since the mode is 1, the M1 M0 bit should be what, 0 1 respectively, right? The M1 bit should be 0, the M0 bit should be 1. The first thing is you need to initialize the TMOD register with mode 1. If you're using timer 0, bit 0 and bit 1 should be set to 0, 1, right? Similarly, what we have, if it is timer 1, bit 4 and bit 5. The bit 4 should be 1, the bit 5 should be 0. Similarly, that is for timer 0. The bit 0 should be 1 and the bit 1 should be 0 there. Next, load registers TL and TH with initial count values. We know that by default what we can have is we can have a value of 0, 0, but you can have any initial count values there. I can start with maybe if it is, since it is mode 1, right, you can start with any values there, right? Maybe 7f we can start, so that what is the maximum value we can have it, ff h there, right? And next what you need to do, start the timer there. How do you start the timer here? By setting the timer bits, tr0 bit or tr1 bit there. You can use the instruction set b tr0 or tr1 to start the timer. Next, once you do that, now the fourth step what you need to do is keep monitoring the timer flag TF with the GNB TFXX target instruction to see if it is raised. Get out of the loop when the TF becomes high. Now what it says is, now keep on monitoring the timer flag. As you can see here in the third step, what we have done here, we have started the timer, right? Now the timer bit is set so that the timers, maybe timer 0 or timer 1 is receiving the clock signals. As it keep on receiving the clock signals, then the timers will keep on incrementing the number of counts in that register, right? As it will keep on increasing, and whenever it reaches FFH, what will happen there? That what, if we can see this instructions, what we know, JNB, jump no bit or not bit, right? JFX6, it will keep on checking whether this bit, the overflow flag, whether this overflow flag is set or not. If it is not set, again it will keep on monitoring the timer flag there, right? And whenever the timer flag is set, and when this timer flag will be set, when the timer has reached its maximum count value, that is FF, right? That value, right? Whenever it is reset, so that now the TF flag will be set there. After that, what you do? You stop the timer. How do you stop the timer? Clear signal. You use the clear instruction, CLR TR0, CLR TR1 instruction. What you use there? Stop the time, clear the, and also what you do? Clear the TF flag for the next round, right? Again, you can see here, if I want, but if because of some reasons the TF flag was set, because of some reasons, you make sure that you confirm that now I will clear that TF flag before the next round here, before the next counting stage here. Again, go back to step 2 to load TH and TL again here, so that I can generate the time delay. Everyone understood this one? Guess you will understand this one when we go through some examples and when we write the ALP program for this one, right? The first one is you should load the TMOD register with mode 1, whether it is a timer 0 or timer 1. For mode 1, what should be the value for M1 and M0? It is M1 is 0, M0 is 1 here. Load the TL and TH registers with initial count values. What could be the initial count values? It can start with 0 or you can have your any initial values, right? You can start with that one, right? And next, start the timer. As I said, how do you start the timer? Set bit TR0 or TR1, right? When you start it, what will happen? The timers will be receiving the clock signals. As it receives the clock signals, it will keep on incrementing the number of counts in the register, and whenever it reaches the maximum value, it resets resets that, you set the overflow flag to 1 there. And also after that, what you do, stop the timer, you clear. And also, when how do you stop? Using the clear instruction, right? And also you need to clear the overflow flag, so that you are making sure that for the next stage the TF flag is not set there, right? And again go back to step 2 to load TH and TL again, right? This is the process what you need to write. If I want to write any C code to generate a time delay using mode 1, or if I want to write any assembly language code, right, for the timer to operate in mode 1 to generate the time delay, these are the steps what you need to follow, right? Now we'll see one program here, one example what we have it there. eh? In the following program, we create a square wave of 50% duty cycle with equal portions high and low on the P1.5 bit, right? The timer 0 is used to generate the time delay, analyze the program. And what is given here, we're trying to generate a square wave of 50% duty cycle. What it says is that in square wave, what we have a on period where the signal is high, we have an off period where the signal is 0 here, right? When I say 50% duty cycle, it means that the on period is equal to the off period here, right? And where we are generating this square wave, we are generating on the port P1.5 here, right? We are using this bit to generate the square wave where the on period is equal to the off period here, right? And the timer 0 is used to generate the time delay, analyze the program. Now here the program is given to us, we will try to analyze this one, right? Right? If you see what are the steps which are followed here to generate the time delay here, as we saw here. The first what we have, load the TMOD value register indicating which timer here. Here what is given, the timer 0 is used to generate the time delay, right? In order to operate in mode 1, what should be the M0 bit? M0 bit should be 1, the M1 bit should be 0. So that what we are doing, we are loading the TMOD register with 0 1 here, hash 0 1. You can write it as H or no, because from 0 to 9 it's still the same there, right? So that you can write it as TMOD comma 0 1 here, so that M0 bit is 1, right? And M1 bit will be 0. What we have when I say 1 here, 0 0 0 1, right? 0 0 0 1. Yeah, bit 0 will be 1, bit 1 will be 0 there, right? Everyone understand this one? What you mean by 0 1 there? Because this is 8-bit register. 1 will be stored as in the lower nibble as 0 0 0 1. So that now I'm making sure that the timer 0 is used and the timer 0 is selected to operate in mode 1. When I say in mode 1, it is 16-bit mode, 16-bit timer. All the 16 bits are used to count the number of clock pulses there, right? Next, what you do, what is the step next we have? Load registers TL and TH with the initial count values, what we have, move TL0 comma hash 0F to H there, right? You can have any initial values. I'm initializing that with this value, right? And move TH0 comma 0FF H here. And here, see, if you can see here, we have used TL0. Why it is TL0? Because timer 0, what we have used in this, the program, what is written, the timer 0 is used to operate in mode 1 there. So that we are using the register TL0 there. And also TH0 because the timer 0 is selected to generate the time delay, right? And what are the initial value which is stored here? This is a higher byte, this is the lower byte. FF F2, what we have, FF F2, right? Next, what we have CPL P1.5. This is complementing whatever the value what we had. Maybe if it was 1 9, now it will be 0. If it was 0, now it will be 1 on this bit, which is a bit we are complementing P1.5. The port 1, fifth bit, what we have, that bit we are complementing now, right? Next, I do something like A call delay SJMP. A call delay means what we have. This is absolute short range call, what we have it. And this is a subroutine what we have written. This is the delay. Delay is nothing but a subroutine what is written there. As everyone understands, if you see the program which is written there is following these steps. First, we are loading the TMOD register. After that, we are registering the TL and TH registers there, right, with the initial count. And here in the example, the initial count what we have is FF, that is the higher byte, and the lower byte is F2, FF, F2 there, right? Next, what we have, and we're complementing P1.5 there, right? And A call delay. Next, what I need to do here, if you see as part of the delay, we have written this, the steps what we have, the third step, right? In this subroutine, this is a subroutine which is written. What is the name of the subroutine we have it? Delay, what we have, right? Delay, what we have, the first instruction what we have, set B space TR0. Why it is TR0 now? Because the timer 0 is used here, right? So that's the reason I need to set this TR0 bit, so that the timer starter bit is set to 1. And this starter, whenever this TR0 bit is 1, what happens? The timer starts here. That's what start the third step what we have, start the timer here, right? Start the timer. Now what we happened? Set B TR0. The timer has started, right? So that now the timer is receiving, right? Now the timer 0 is receiving the clock pulses. As the number of clock pulses increments here, the number of counts in the timer 0 also increases there. Now next what I do, again J and B TF0, right? Again it is TF0. What is this? If there is an overflow from the timer 0, right? That's the reason we have selected the bit as TF0 there, right? Jump no bit, right? It means that it has to execute this instruction. It has to execute this instruction key again and again till the bit is set to 1 there, right? Since the bit is not set here, what will again it will keep on monitoring whether the overflow flag bit is set or not. Now what happens? The counter will keep on increment. You can see the initial value what we had in this program. What we have, the higher byte is FFH, the lower byte is F2, so that the initial count what we have it in the register what we have is FF2 there, right? As the number of clock pulse increases, the first clock pulse it receives, right, it increments the value. It increments by 1, so that it is FF3 now, right? Now it has not set the overflow flag, because the maximum value what we can have it is FFH there. Again it receives the clock pulse, and again it will, the count in the timer 0 will be incremented by 1. Now it will be FFF4, and it will keep on incrementing as it receives the number of clock pulses, and the maximum clock pulse what it counts is FFFF here, right? And whenever it is FFF, what will happen? It will reset to 00, right? That register, the timer 0 will be reset to 00. At that time it will set the overflow flag to 1 here, right? That's what is happening. It will keep on checking for that flag, whether that flag is 0 or not. As the number of counts increases for the timer 0, and whenever it reaches FF, the maximum value, right, FF there, what will happen? It will reset to 00 file, and it will set the overflow flag to 1 there. And once the overflow flag is set here, what will happen here? It will come out of this loop, right? It will no more execute the JNB instruction. It will come out of the loop, and here it will set clear TR0. What do you mean by TR0 here? It will stop the timer 0 there, right? And again clear TF0. You're making sure that this flag is again set to 0, so that if you're still running it, this program, right, if it is a continuous program, you're making sure that this flag is again reset to 0 there. Again you have return there, right? Where when I have return, for every subroutine what you have a return instruction there. It will return from this one, right? It will go back here again. What is the next instruction what we have? sjmp here. Again it will go to here, move TL0, 0 F2H. Again move, so that if you can see here, maybe take an example that before, when we're executing this one, the p1.5 was equal to 1. For how long the p1.5 is equal to 1? It all depends on the delay function what we have it, right? The time which is required to count from here to here, right? That time the port 1 will have a value of logic 1 there, right? And whenever it comes out of that loop, what will happen? Again these two registers are initialized with this initial value. Again you say complement p1.5, so that the p1.5 will be set to 0 now. Now that is equal to 0 now, right? Since it is 0, for how long the p1.5 will be 0? Till you call, till you come out of from this subroutine function, the delay function what you have returned it, right? The time required in order to execute this subroutine, so that from ff0 to ff here, right? Once it comes back, for that long the p1.5 bit will be 0. Again it will be complemented with 1, and again that value will stay for 1 till this delay here, right? We can change the delay of this one depending on the initial value what we set here, right? Higher value what we give it in this one will happen, the delay will be less. If we start with 0 0, what will happen? The delay will be more there, so that for longer time the bit will be set to 1, or for longer time the bit will be set to 0 there, right? Right, this is what we have. First thing what we have, in the following program we create a square wave of 50% duty cycle. The timer 0 is used to generate the time delay. Analyze the program. Everyone understood this program, what is given here? If you see how the program is written, it has followed these steps here. First, load the TMOD registers with the mode bits. Again initialize the TL and TH 8-bit register with the initial count values. You can start with any initial count, right? And start the timer there, right? You can use the set B instruction to start the timer, and you keep on monitoring the flag with the help of this JNB instruction, and you stop the timer by using clear instruction, right? This is a process which is followed. Now for this one, now for this program, since it says analyze the program, now you need to calculate the amount of time delay in the delay subroutine generated by the timer. And here the crystal frequency is given as 11.0592 megahertz. 11.0592 megahertz here. Now you need to say how much is the time